Starting off with grade 11 vectors. So let's look at quickly a definition of vectors, or resultant vector rather. So a resultant or a net, often we're asked to work out the net force or the resultant force, which is the same thing. The resultant is this vector sum of two or more vectors, or the single vector having the same effect as two or more vectors together. So that's your definition. So let's use an example and explain what that means. So in grade 10, you were given questions where, let's say you walked 20 meters to the right and then 10 meters downwards, and the question asked for the displacement of this person. And your displacement is the shortest distance from your starting point to your end point, okay? And that is the start of vectors. So this one vector has the same effect as the other two vectors combined. So if someone looked away, to them it just looks like you took this route, this dotted line route. Okay, so it's the single vector having the same effect as two or more vectors combined. When it comes to forces, okay, and let's use a little practical example. Example number 1. If we had a box and someone pulled that box with a force of, let's say, 30 newtons to the right and 40 newtons downwards, and they asked us to calculate the net force on the box, or the resultant force on the box, what they're asking us to work out is the single force that has the same effect as two or more forces combined. So in this case, you can imagine that this box, if I pulled it to the right and someone else pulled it down, would move sort of in this direction at the end of the day. So what we have to do is we have to redraw these forces into a vector triangle. And the way we draw them is called head to tail, head to tail. So that means the way it's drawn at the moment is not the correct way. We have to draw them where the first one ends, the next one starts. So the 30 newtons, and then where that one ends, the next one starts. So the 40 newtons here. Obviously, you can draw the 40 newtons first and then the 30 newtons. Okay, there's no right or wrong way. It's your choice. I tend to always just draw my triangles a specific way, but it's up to you which one you want to draw first. It doesn't make any difference. If you think back to grade 10 and displacement, whether you say this person walks to the right and then down, or down and then to the right, your displacement vector will still be the same at the end of the day. So we are now going to work out the single force, and let's grab a different color here, the single force that has the same effect as the other two forces combined. So the type of triangle you're going to draw when it comes to working out Fnet is what we call an open vector triangle. And that might not mean much to you until we get to other types of examples where we draw closed vector triangles. But at the moment, open vector triangle means you draw your triangle head to tail, then you pick up your pen and you draw your Fnet tail to tail and head to head using a ruler. Let's try to draw that a bit more straight. So Fnet would be here, or F resultant would be here. And that is the single force in this case. It doesn't have to be force. Vectors could be distances, it could be force, okay, it could be electrostatic forces when we get to that section. So it's the single, in this case, force that has the same effect as two or more forces, or in this case, the two forces combined. Okay, so I chose these numbers because they're nice and simple. So if we work out Fnet, we could do Pythag here, because these forces, and my diagram should just show actually that that's 90 degrees as well. My Fnet, and show all your little working out, is equal to, let's say, force 1 squared plus force 2 squared. Always just write a little formula just in case there's marks allocated for something like that. So 30 squared plus 40 squared, and you would have seen this in math before. If you want to get Fnet by itself, you square root, and this is a nice value. It works out to be 50. Okay, 15 newtons. Now we know, hopefully from grade 10, that force is a vector. Okay, in other words, it's a physical quantity that has size and direction. Compared to scalars, and scalars are physical quantities that only have size, no direction. Okay, examples of vectors are, since we're at this section now, force, okay, displacement, velocity, which we won't see in this section, but we might as well talk about it. Whereas scalars could be something like mass is a scalar, it doesn't have direction. Speed, you can just say I'm going 20 kilometers per hour. Whereas if I ask you for your velocity, you'd say 20 kilometers per hour west or left or whatever. Okay, distance. These are scalars. They don't need direction, they only have size, whereas vectors need size and direction. So force is a vector. Whenever we work out force, no one has to tell us work out the size and the direction. We should know that if something is a force, it needs both a size and a direction. Okay, so which means I need a direction here. So I need to figure out, and what I'm going to do is I'm going to work out the bearing. We need to figure out the angle that this force will end up pulling at. So what we do, and there's lots of ways to measure this. Some books measure it from the x-axis, from the y-axis. Okay, I'm always going to do bearing, which means I'm always going to draw a Cartesian plane, okay, where my two tails meet in this case, and my theta will always go again where the two tails meet. Okay, let's make a note of that. When working out Fnet, okay, when calculating Fnet, okay, draw theta and your Cartesian plane where the two tails meet. Okay, you're going to see it's not always going to be the case that there will be two tails. When it comes to Fnet, there will in fact always be two tails. And you can always draw your Cartesian plane at the two tails, and same for your theta. And now we're going to work out the bearing. Bearing means from north, measured clockwise, until you get to your dotted line, which is why I like making this a different color or a dotted line. So from north, clockwise, okay, and bearing, okay, if you've just done trig or something, this is going to be a little bit strange, but we're going to work clockwise. So 0 degrees there, 90 degrees here, 180 here, 270, and then 360 degrees ending off here again. Okay, so if you're doing from, and you don't have to do bearing, it's just the way that I always do it. Bearing is from north clockwise. So to do that, I'm going to go 90 degrees plus the theta there. That would give me my bearing. In other words, that would give me that entire orange angle there. So I will go therefore, because I want to finish off this question, and I need to say Fnet is, I need to make the person who's marking aware that I understand force is a vector, it needs size, and it needs direction. So I'm going to say 50 newtons at a bearing. Okay, now I don't have that theta yet, so we're quickly going to work out that theta on the side here. Okay, so we can use SOHCAHTOA. It is a 90-degree triangle. And I've got my adjacent. Obviously, adjacent opposite is to do with which angle's perspective you're looking at it from. If you're looking at this angle, this is my adjacent and this is my opposite. Whereas if this was, let's say, your angle, then this is adjacent or next to the angle, and this is the opposite. So be careful when deciding, you need to look at it from that angle's perspective. So from this angle's perspective, this is adjacent or next to it, this is opposite. The hypotenuse never changes, that's always opposite the 90-degree angle. Okay, I'm going to try and not use the hypotenuse. Just in case I made a mistake in the hypotenuse, I'm always going to use tan. Okay, that way I don't carry on my mistake here. So always, again, write your formula. So tan theta is equal to opposite, which is the 40 over the 30 degrees. Okay, and if we work that out, okay, you press shift tan on your calculator because you want a theta. We always press shift tan or arctan, and then theta turns out to be 53,13 degrees. Okay, so that angle there is 53,13. Then to get your bearing, like we said, you'd say 90 plus the 53. Okay, I like writing my working out in a little bracket here. So I'm going to say the bearing is 90 plus the 53,13, which gives me 143,13 degrees. And that is my final answer. Okay, if I just end with the red writing, then I've done the force and I've done the angle, but I haven't done the final answer. Okay, I need to, force is a vector, it needs size, and it needs a direction, which I'll always do as bearing. Okay, so remember, we just worked out the single force that has the same effect as the other two forces combined. So instead of two people pulling this box, one with a force of 30 newtons to the right and one with a force of 40 newtons down, one person could pull this box with a force of 50 newtons at this bearing, and it will have the same effect as the other two people combined. Okay, I'm going to put a second question up. Take some time, pause the video here, and try and work this out yourself. Okay, so if someone pulls the box with a force of 50 newtons to the right and then 80 newtons down, what would be the net force or the resultant force on this box? So first of all, you can imagine the box is going to move in this sort of direction, somewhere between the two forces, probably more towards the side because this force is the bigger force. But that's sort of the direction I'm expecting. If I end up getting an answer and it's something like in that direction or that direction, I'm going to get very worried because it makes no logical sense that if you pull a box to the left and down, that it won't end up going somewhere between those two forces. So pause the video here, take a second, and quickly work that out. Okay, so let's start by drawing the triangle. So 50 newtons, and try and draw your sketch to scale as best as possible. What I mean by that is maybe take a 5 centimeter line to draw this and an 8 centimeter line to draw this. It just gives you a bit of an idea once you get your answer if your answer is making sort of sense. Okay, then where that one ends, the next one starts. So head to tail, head to tail. So obviously my 80 newtons force needs to be longer than the 50 newtons force. Okay, so that's 80 newtons. Okay, so that's head to tail, head to tail. Pick up your pen, and if you're looking for F net or F resultant, it's tail to tail and head to head. In other words, start your F net where the first force started and end your F net where the last force ended. Put your theta where the two tails are. Put your Cartesian plane where the two tails are. Okay, then we're going to use Pythag to work out F net. Okay, always remember to write a little formula, get into a good habit from the beginning. Okay, it doesn't matter which one you make, F1 or F2. Okay, if you work that out, remember to square root at the end. If you get a very big answer, then you've probably forgotten to square root. Always check if your answer sort of makes sense. We are working out the hypotenuse, so it should be bigger than the 50 and the 80 newtons. Okay, which makes sense. We're getting 94.33. Now, if you're not going to use that answer yet, it's a good idea to round off now already. Okay, if you're going to use sine or cos to work out theta, then don't round that off just yet. Okay, but I'm going to try, like I said, to avoid using cos or sine just in case I made a mistake in the hypotenuse and then I carry on that mistake further on. Okay, so I'm always going to use tan theta, okay, is equal to opposite over adjacent. So from this angle's perspective, this one at the top here, the 50 newtons is adjacent or next to that angle, and the 80 is the opposite. So we go tan theta is equal to the opposite, okay, over the adjacent, and we end up getting 57.9946. So we can make it 57.99. Okay, working out the bearing is not going to make a difference to this. Then let's grab our orange pen here. Now the angle we're looking for is the bearing measured from 0 or from north clockwise until you get to the dotted line. So that line there. So how are we going to measure the bearing? We're going to say 90, 180. Now I'm about to just do a little exercise with you of just working out bearing because I find that's what people struggle with the most. Now ask yourself which side or which line is this triangle touching? Is it touching the 0 degrees, the 90 degrees, the 180 degrees, the 270, or the 360? So in this case, it's touching the 270 degree line, and it's not going beyond that. It's just short of that. So we're going to go 270 degrees minus theta to get our bearing. Okay, so don't forget at the end to go, therefore, F net is 94.34, we can round off, at a bearing of, I'll put my working in a little bracket here, at a bearing of 270 degrees minus 57.99, okay, which gives us 212.01 degrees as our final bearing. If you drew the triangle differently, if you drew down first and then to the left, okay, and I'm going to be careful to draw it more in proportion, then your Fnet looks like this. You'll obviously still get the same 94.3398 newtons. However, for your angle, okay, your theta is different. Your theta will actually be 32.01 degrees if we round off. The reason for that, and this is not something you'll see because you won't draw the triangle two ways, that's a waste of time. But if you look at this triangle and this triangle, let's actually draw it in here. Okay, what this is, this triangle is going to fit in here on that sketch, and that theta will fit in here. Okay, so in fact these two angles will always be complementary. They'll add together and give you 90 degrees. So and that's obviously on purpose because they'll always fit in the same quadrant there. Okay, one is just touching the 180 degree line, one is touching the 270 degree line. If you drew your triangle the way that I just drew, then your Cartesian plane goes here, and then your bearing would be 180 because it's touching the 180 degree line, plus one of my students said something very clever. She said, if you're bearing this orange line here, orange angle, doesn't go through theta, in other words, it doesn't cross into that angle, then you're always going to say something, in this case 270 minus the theta. And if you look at the sketch on the right hand side, my actual orange angle crosses through theta, then you're always going to say something plus theta. In this case 180 degrees plus theta. But let's take a second and just quickly just draw some angles on our Cartesian plane, and let's figure out when will we add or subtract and why to get the bearing. I find in this section people don't really struggle with the trig. It's drawing the triangles that can get tricky, and it's working out the bearing that can get tricky. Okay, so draw your Fnet in as a dotted line. Just makes it a lot more obvious to where you're going when you draw in that orange Fnet. Okay, so if we look at this here, so let's mark our theta where the two tails are. Okay, if you look at the first one, your actual, let's just draw 0 degrees, 90 degrees, 180, 270, and 360. Okay, so this triangle is touching the 0 degree line, so it has to be 0, and it's actually the orange angle is going into theta or crossing across theta, so we say 0 plus theta. Okay, if we were to work out the second angle, okay, so from north or from 0 degrees until you get to the dotted line, okay, first of all, that angle, or that triangle, sorry, is touching the 90 degree line, so it'll be 90. That angle is crossing over theta, so it's 90 plus theta. Okay, then the next one, okay, it's touching the 270 line. It's not crossing over the line, it's not crossing into theta, so it's minus theta. And then the last one is going to be 0 all the way to here. It's touching the 360 line, so we'll go 360 degrees minus theta because it's not actually crossing into the line, and that will give me my bearing for that one. Okay, I'm going to draw a third example. Again, you might want to pause at this point, just work it out for yourself so you see if we get the same Fnet. Remember, you're not just working out a force, you're also working out an angle. Okay, so don't stop until you have the size and direction. Force is a vector. Okay, so the next example has got someone pulling a box with 20 newtons up, and a second person pulling a box with 100 newtons to the left, and your question is still to work out your net or resultant, same thing, force. And you can imagine again, your force is going to end up looking something in that direction. If it's not, then something isn't right. Logically, that doesn't make sense. Okay, so if we draw a triangle, we're going to draw, I'm going to keep saying open vector triangle, which again might not mean much to you until we get to closed vector triangles, but it's what we always draw, open vector triangles, when we work on Fnet or F resultant. So we draw head to tail, pick up your pen, okay, draw your Fnet tail to tail and head to head using a ruler, and then you get your Fnet. You could also draw the triangle where the object goes to the left first and then up. Try and draw your forces to scale. Okay, this 100 Newton line needs to be like 5 times the length of the 20 Newton line. It doesn't have to be exactly to scale, but it just helps a little bit for you to imagine whether your answer makes sense. Okay, you can see your Fnet arrow looks the same. If it didn't, I'd get worried. Not that you would do both in an exam or a test. There's your theta at the two tails. There's your Cartesian plane at the two tails. Okay, I'll work with my triangle on the left-hand side. Okay, but if you work with this angle, you just need to check if it's complementary to the angle I get. So if this one's 70 degrees, the other one would be 20 degrees. Okay, just if you want to do a quick check. Okay, so first of all, we'll do Pythag. Okay, when you do Fnet, okay, I'm going to speed things up a little bit as we're getting the hang of this. Once you do Fnet here in Pythag and you square root, you should get 101,98 degrees. Then your angle, again, I'm going to work with the sketch here. My tan theta is opposite over adjacent. So tan theta, from this angle's perspective, this is my adjacent and this is my opposite. Okay, so we'll go tan theta is equal to 100 over 20. We'll shift tan and we should end up getting theta equal to 78,69 degrees. Okay, which means if you're drawing your triangle like the right hand side, okay, then you should get theta as 11,31 degrees. Okay, then your bearing. To get your bearing here, you go all the way here. It's touching the 360 line, but it's not going through theta, so we say 360 minus theta. Bearing on this one, first of all, your triangle is touching the 270 line, and your orange line angle is crossing in through theta, so you say plus theta there. Okay, so we mustn't forget to write the final step. We write therefore Fnet is equal to 101,98 newtons. Okay, sorry, that looked like a degree there. That's in fact newtons at a bearing of, let's just do a little working here, 360 minus 78,69. Okay, which gives us a bearing of 281,31 degrees. Okay, now let's take this opportunity while this is up on the board, okay, to imagine if the question was asked differently, how we would approach this question differently. Okay, so the initial question was to calculate the force, the net force, if two people were to exert forces on an object like this. If the question was very different though, and it asked you to calculate the force, let's write this down, calculate the force needed to keep the system at rest, let's say to keep the box at rest, that's a very, very different question. Okay, so let's go back a second to our original. So if two people were exerting a force on this box, it would end up going in this sort of direction, probably leaning more towards the 100 Newton because that is the bigger force, and we did see that, something like that. That would be your Fnet. Now if you think about it, that Fnet was 101 point something, 101.98 newtons. 1.98 newtons. That would be the net force acting on the box. If the question was work out the force that you need to keep the system at rest, in equilibrium, stationary, whichever word they choose to use, what you're trying to figure out is, instead of two people pulling a box like this, what force could a third person exert to keep this box perfectly stationary? Now, some people see it straight away and they realize that, well, if this is the net force, remember that's the force that is needed to replace the other two forces. So the other two are gone now. So if you want this box to be stationary, you need to exert a force the exact same size in the exact opposite direction, 180-degree difference, to the original Fnet in order to keep this box at rest. Because now what's happening is your two forces will cancel out and this box will end up what you call an equilibrium. Now, what implication does that have for the triangle we draw in order to solve this? So remember we said before the triangles you're drawing are called open vector triangles. In other words, head to tail, pick up your pen, and then tail to tail, head to head. Now you can imagine if the force that's necessary to keep this box at rest is in the exact opposite direction, surely we can make this work in the triangle. We just have to draw our triangle differently. So what we do now is the minute something is at rest, let's use a whole bunch of different words. Stationary, at rest, in equilibrium. Now, okay, instead of drawing an open vector triangle like we used to do with Fnet, we now draw what you call closed vector triangles. Okay, anything to do with stationary, equilibrium, at rest, anything like that in the question. And we change our whole approach and now we draw closed vector triangles. Okay, so what does that mean? That means when I draw my forces, okay, and let's try to keep the sketch here so we can picture it. We're going to draw head to tail, sorry, let's start with this one, head to tail, and now, instead of picking your pen up and starting tail to tail, head to head, you are now drawing this orange line in. So you draw head to tail, head to tail, head to tail all the way. Okay? And now your theta that you're working out will go at the tail of the force you're calculating, which is exactly what you did before. It was at the tail of Fnet, because that's the force that you were working out. Okay, but it was very obvious because there was two tails that met each other. Whereas here it's not so obvious, but it's at the tail of the force that you're calculating, and so is your Cartesian plane. Put it at the tail of the force that you are calculating. Okay, what does that mean? Well, it means it's the exact same size. We'll still use Pythag. However, your angle is now different. Now it's 180 degrees off of the original, but instead of working out the original and adding 180 degrees, we'll go from scratch. We'll draw a triangle like this, and now we'll work out that angle. You'll approach the question completely differently. You'll actually draw what we call a closed vector triangle, okay, where you don't pick up your pen, head to tail, head to tail, head to tail all the way, and you work out that theta on that closed vector triangle. And when we do that, we get 11.31 degrees here for our theta. And then in order to get our bearing measured from north clockwise, we will go 90 degrees plus theta. Okay, and I'm going to call this force something different. I'm going to call it the Fequilibriant. In other words, the force needed to keep the other two forces, or to keep the system rather, at rest, is 101.98 newtons at a bearing, and I like showing my little working out in bracket, of 90 plus 11.31 degrees, okay, which gives me 101.31 degrees. Okay, so very similar, obviously the same answer in the force, and your angle is different, and you're drawing an closed vector triangle instead of an open vector triangle. Okay, I'm going to give you another one to do. Pause the video for a minute and try and work out now no longer Fnet, but we are now working out Fequilibriant. So the question's very different. Okay, so let's make this 60 newtons and 50 newtons. And the force is now asking you let's just write it here, what force is necessary, or calculate the force necessary to keep the system at rest. Okay, so pause the video here for a second, try and work it out. Remember that the minute you see the word rest, equilibrium, stationary, held in position or anything like that. You are now changing your approach. You're drawing a closed vector triangle. Okay, so let's draw that triangle. So first of all, head to tail, head to tail. Again, you can start with this one and do that one. That doesn't matter. Okay, but head to tail. Let's use a different color pen. Head to tail, head to tail, head to tail, all the way. Put your theta where your tail of the force that you're calculating. Put your Cartesian plane there. If we do Pythag here, same approach as we would do before. Okay, I think you'd be comfortable with Pythag now, so we're just going to go straight to the answer. It's 78.10 newtons. Okay, and my bearing. Okay, so this was my 60 and my 50. If I'm looking at it from this angle's perspective. Okay, then we're doing tan theta is opposite over adjacent. And that gives us 50.19 degrees. Okay, but to find our actual orange angle here, we'll have to say 360 degrees minus that theta. So therefore, F equilibriant force, in other words, the force needed to keep the other two, or to cancel out the other two, or to keep the system at rest, is 78.10 newtons at a bearing of, let's just show the little working here, 360 minus the 50.19. Okay, which gives us an angle of 309.81 degrees.